my original sequence. This is my genome. Okay? So the first thing we do is we break it down and we get reads from it, right? Let's say that the reads are, I don't know, 10 characters long. Or no, just make it 5. Okay? And we start doing this process over and over and over until we have a lot of coverage of this genome. Yeah, this small phrase, I love bioinformatics, we have sampled it and transformed it into reads, yeah, that are overlapping, they overlap each other and maybe they even repeat each other. Yeah? But now, what we've got, each fragment that we're getting, the entire sentence is your genome. All right? That's your genome. When you break it down in the lab and you produce your library and you sequence it, yeah, each fragment of each 5-letter fragment that you get here, that's your read. Yeah, and you're going to get reads that are overlapping to each other, and you're going to get enough coverage in the reads to actually kind of make sense of what the original phrase was or what your original genome was, right? That was the idea behind the OLC approach, is that you have enough of these 5-character fragments, reads, yeah, that you can find overlapping regions between them. You can score them. You can put together those that have highest score, and you can put apart those that have the lowest score, and kind of make a path along your alignments. Yeah? But the more reads you have, the more comparisons you have to make, and therefore this isn't as feasible anymore. So, what they do what the assemblers do in the bridging graphs is they further decompose each of those reads. If each of those reads is already small in comparison to the original genome or to the original phrase, yeah, the bridging graph decomposes it even to smaller pieces, which are called k-mers. All right, and each of those 5-character reads, is decomposed in smaller, contiguous, overlapping fragments called k-mers. Let's assume that we want to use a k-mer equal 3. That is 3-character k-mers. Yeah. So the first read, it would become this. It's not very obvious, yeah, but you have converted that 5-character read into 3 k-mers of 3 characters each. First you have the I space L, then you have the space LO, and then you have the LOV. And you know that they are contiguous because first you got them from the same read, and second, because they share at least k-1 sequences, similar. For example, the first k-mer and the second k-mer, they share the space L. The second and the third, they share the same LO and LO. And that's the process you're going to repeat for every single read in your data set. The idea is that the path that you generate from decomposing the reads in those small k-mers is going to be identical to the path you would get if you were to decompose the original sequence, the original phrase, into k-mers the same size. That is the idea. How do they put this into in a computer? Basically, they do it like they were showing it here. This is the decomposition into a trimer. Yes, each of the reads has been decomposed into fragments, smaller fragments called k-mers. In this case, these are 3 base k-mers. Yeah, and since we already know that these k-mers belong to the same sequence, to the same read, we can say, okay, there is a connection between them. They are overlapping. And this is where the second read comes in. The second read, for example, in this one, the second read is of B, right? And if you do the same, you'll see that you have first OB, then you have these 3 k-mers or 3 trimmers, right? But there is a thing, because the original reads had an overlapping, Yeah, they also share some k-mers. For example, OBE shares k minus 1 characters, which is k minus 1 would be 2, k minus 1 characters in common with this one, LOB. The OB is repeated here. So when you start building the graph, since you already forget, after you decompose into k-mers, you forget that they used to belong to the same read. Yeah, you automatically, the algorithm automatically generates another edge that is contiguous to this one. You generate an arrow going in that direction. Say, yes, these two share k minus 1 bases in common. Yeah, so they can be attached together. Yeah, and then as more reads are added, there are two things that are going to happen. The graph is going to become more and more complex because you're going to start having more and more connections in different ways, and each of the nodes will have a number of times it's being seen. You will record how many times these nodes have been seen in the data set, because that's going to help you differentiate between errors in your data set and actual sequence, actual k-mers that belong to the real sequence. How? Because errors in Illumina sequences are very rare. And that means that if one sequence has an error, the other sequence that overlap it don't. Yeah? And if you find one read that has an error, the most likely scenario is that the k-mers that are produced from that read will not have the support of the k-mers that are produced by other reads from the same loci. So the coverage of that k-mer will be very, very low. Usually it's just one. Yeah, it's a k-mer that appears only once in the entire data set, in millions and millions of reads. What's the probability of sequencing a whole genome hundreds of times so that you get millions of k-mers, and that one of the k-mers only appears once in the entire data set? It's very low. It is very, very low. And that's how you pick up sequencing errors. And that's how you start, for example, that's one of the steps how you start cleaning up the mess of graph that you have. You say, okay, all those that have very low coverage or a coverage or a redundancy that doesn't match the rest of the k-mers, which have maybe 30 or 40 times, they appear 30 or 40 times in the data set, they say, yeah, if this appears only once, very likely this is an error, a sequencing error. That happens in one read and we never saw it again, so we can just get rid of this branch of the graph because it's more likely erroneous. Then you have other problems, and this is where repeats come into play, because since you are reducing the size of the comparisons you're doing, you're not comparing whole reads, you're comparing just the k-mers. The repeats can only be solved if they are smaller than the k-mer that you chose. That is, if you have a repeat in the original sequence that is longer than the size of the k-mer you chose, you won't be able to solve it. You won't be able to know what comes before and what comes after. It will be collapsed into a single node. And when it's collapsed to a single node, also the other problem is that two different paths can take you in loop to the same spot. Why? Because you have a repeat on that spot. I think this one actually shows that. Yeah, look at this cycle here. You can go this way, or you can also go this way. You see how CGA has a 2 bases overlap with GAC, which has a 2 bases overlap to ACG, and this one at the same time has a 2 bases overlap not only to the original CGA but also to CGT, the CG. So you don't know exactly what path to follow in this graph. What is the correct path? Those are bubbles. Yeah, they can be generated by sequencing errors, which can be identified, but also by heterozygosity. Just one heterozygous SNP in your sequence, yeah, will cause these kind of bubbles. You won't be able to know how to solve it. So yeah, I think that's the most basic way I can explain how the bridging graphs work. In comparison to OLC assembler approach, yeah, this takes a lot less time. because you just generate, you just keep a record of what k-mers have you seen, what are the connections between the k-mers, depending on those k-1 overlaps between all the k-mers in the data set. Yeah, then you keep a record of the redundancy of each k-mer. Yeah, and that way you start cleaning up all the paths that you've created and try to make sense of it. Try to transverse the graph until it kind of feels better. But yeah, there are limitations. Since you're using k-mers, you're getting rid of a lot of information. For example, the original connections within the reads. Also, you're getting rid of paired end data. If you had two pairs that used to belong to the same template DNA, and you decompose all of them into k-mers and do a debridging graph, yeah, the debridging graph, well, the original ones didn't have a way to record that these two k-mers used to belong to the same template of DNA, so they should be somehow together. And that's why they started doing scaffolding, because after they finished the assembly, since they had forgotten during the assembly and during the contigs production the origin of each of the k-mers that was producing the contigs, yeah, they would map the reads back to the contigs, yeah, and try to understand, hey, yes, so these two reads are paired ends. There is enough evidence of a lot of paired ends mapping to these two different contigs, yeah, so these contigs are probably together physically. Even though the graph didn't actually solve it, didn't actually solve the intermediate steps between those contigs, because there was probably repeat, a lot of heterozygosity, etc. It's getting really hot, isn't it? Can somebody tell him to turn on the aircon? Or this one. If you're too cold back there, maybe this one. But anyway, since they have forgotten in the original graph which pairs of reads belong together and therefore which contigs should have belonged together, they use mapping of the reads back to the assembly to find again those relationships and to build what they call scaffolds. And that's where the scaffold naming came from. The fact that the debridging graph didn't save the paired information and it had to be put back into the assembly by a post-processing of the assembly. It was a post-processing part of the assembly, an extra step. Other challenges of debridging assembly or debridging algorithms are uneven sampling of the genome. That is, uneven coverage of the genome. Because depending on the k-mer size, yeah, it will have an effect on lower coverage or low coverage regions that haven't been sampled during the sequencing process highly enough, yeah, will need a bigger k-mer sizes to actually make a contiguous sequences. If you choose a small k-mer size, yeah, those regions that weren't sequenced deep enough, yeah, they will appear fractured, and that's because you don't have those small k-mers close enough to actually keep building the contiguous overlapping graph. The other problem is that by forgetting the original relationship between of the k-mers within the read, yeah, you also are more prone to misassembly. Regions of the genome or separate regions of the genome that have repeats may end up being attached together because they look too much like each other. More often than not, the assemblers deal with this by every time they find a complex or like a repeat in the genome, something that has way too high coverage compared to the rest of the k-mers, and that has too many connections, too many ins and too many outs, it just breaks it down, and that decreases the contiguity of your assembly, because the repeat region is going to be put in a separate contig, and the surrounding non-repeat regions, yeah, are going to be put in separate contigs as well. Two loci that could have been clearly put together with a single repeat in the middle and the surrounding non-repeat regions, yeah, they are break down into 5 loci. Two that 4 non-repetitive and 1 repetitive, because you cannot tell which way is the right way of solving that repeat. And that takes us to the last assembly algorithm. The idea is similar to the one in the debridging graphs. Yeah, the only thing is that you don't use a single fixed size k-mer to build a string graph. Yeah, you use kind of like a variable size k-mer to build the string graphs. That makes it easier to handle uneven coverage sequencing. For example, transcriptome data, which has a lot more sequencing of some transcripts than other transcripts. Also metagenomic data, which has a lot more abundance of DNA from bacteria or from species that dominate a community compared to those that don't dominate the community. So the string graphs handle those much better. But the caveats are the same. If the repeat regions are longer than the read length, yeah, there is no way to solve this. In the graph. And therefore, you're going to have a more fractioned assembly. So you see, the main challenge in all these assembly algorithms is repeats. And the only way to tackle them is to get, usually, longer reads. Longer reads is the only way you can, longer reads or longer insert sizes is the only way you're going to have to actually solve big repeats in the genome. Currently, yes, diverging graphs and sting graphs are the most popular for short read assembly. OLC, overlaid layout consensus are the most popular algorithms for long read sequencing, nanopore and PacBio. Now there are some algorithms that are actually pretty good that are using diverging, a special kind of diverging graph because there is not one single kind. You have like 10 or 15 different kinds of diverging graph and different ways of putting the data in the computer, saving the data in the computer. But right now they're using what they call repeat graphs, which is a variant of the diverging graphs that is specifically designed to be used with error-prone long reads. So it's kind of using diverging graphs, but taking into account the high error rate they have modified the diverging graphs to make them useful for genome assembly of long reads. And that's kind of faster, more memory efficient, but they are still not as accurate as the overlaid layout consensus for the long reads. So let's go to the essential steps. And this is where we can start our practice. Yeah, let's go to the essential steps. And there are 4 very clear essential steps when you try to tackle, or when you try to do a whole genome assembly. Most of the steps are going to be common between every single pipeline bioinformatic analysis that you will find. The first step, once you receive your raw FASTQ data, yeah, is to do a quality control. You want to see what's the fraction of your reads that has a poor quality. You want to see if you have overrepresented sequences that could be adapters, or you want to see if you have contamination from the library production step. All these things are things that you want to see. Yeah, you want to make sure that the data you're going to start working with is as clean as possible. Is what you needed to start with the follow-up step. Once you identify what's wrong with your data, yeah, you start getting rid of of those things that are wrong with your data. If you have way too many low-quality bases, you remove them from your data. You cut them off. If you found that you have still sequencing adapters in your data, you know that those sequencing adapters at the time of assembly will look like repeats because they are going to be the same in many reads. You have to remove them. So you chop them off. Also, in some assembly pipelines, they use this step at this point here to do some k-mer analysis. K-mer analysis that they use sometimes to, instead of removing the low quality or erroneous k-mers, to correct them based only on the frequency of k-mers that they see in the dataset. If they see a k-mer that has a multiplicity of 1, that appears only once in the entire dataset, automatically is classified as erroneous. Yeah, and then you look the closest k-mer that has the appropriate coverage. Let's say that the average coverage of all k-mers is around 30 or 40. And you have one k-mer that has one single base pair different with that k-mer that had only one coverage. Then what the corrector assumes is that the sequencing, that k-mer that only had multiplicity of 1, had an error. That error was that SNP you just found. Yeah, and what they do is they correct that single base pair and put it and convert it back into the main k-mer, the one that has high multiplicity. I think you shouldn't do that at all. You should just get rid of those low multiplicity k-mers. But there's an argument to be had about, yes, why not correct them? I think you would be biasing your data towards those things that are more frequent in your data, but that's up to debate, I guess. So the k-mer analysis also gives you a bunch of other information. That other information is what we were discussing. It's not only the number of erroneous reads, but also the amount of heterozygosity in your data. Heterozygous loci are going to appear to have less coverage than homozygous loci. Because for each homozygous loci, you will always have two reads supporting the same k-mer. For each heterozygous loci, you will have only one. Why? Because the homozygous loci will have one read from the paternal chromosome, and another read from the maternal chromosome. Whereas the heterozygous regions, the heterozygous k-mers, will have only one read, either from the paternal or from the maternal. But the paternal and the maternal are not going to be the same because they are heterozygous. So right now, the first thing we're going to do is explore our FASTQ sequences. We're going to do the quality control. And for that, we're going to use a tool called FastQC. It's going to produce an HTML result that you will be able to open in any Internet Explorer. Firefox. Firefox is my favorite, alongside with Chrome. But you can open it with any Explorer. So let's go to your machines. We were here. So we have the SIM1 FastQ and the SIM2 FastQ. The first thing you have to know is that the FastQC program is already installed on BioLinux. So if you write FastQC and press enter, well, you should have that. There you go. It takes a little while. You'll get a graphic user interface. But other than that, no. So you guys can use either the user interface, where you can say open, then you will navigate sim1.fastq, okay, and you will start the analysis, just as simple as that. Go to file on the top. Do you all have the FastQC user interface? Yep, exactly. So it gives you the first, you'll see that there's kind of a menu on the left side, and it'll tell you, hey, first basic statistics, the name of the file, the file type, what's encoding, because there were several different kind of encoding back when base calling was an issue. It's not anymore. The total number of sequences, how many sequences were filtered before even being analyzed, what's the sequence length, the average sequence length of all the sequences, 100 base pair, what's the percentage of the GC content? Yes, 38%. So let's go through each of the tabs to understand what it means. So this is the per base sequence quality. Basically, what it's telling you is what's the average quality in all your data set, for each of the bases in the reads. So in position 1, the x-axis says position. It's the position. I did that on purpose. Yeah. So it gives you the position in the read. So on average, on position 1 of all the 1 million reads, you have an average quality of around 36, which is where the red line is. And you have a lot of standard deviation that goes from 30 all the way to, well, 38. I guess it's the limit at this point. That means that in position 1, the chances of getting an error are between 1 in 1,000 and 1 in 10,000 base pairs. So it's it would be very rare to find an error in this sequence. Yeah, you can keep going down the sequence, yeah, and you'll see that for position 2, the things, there's a little more deviation, but it's still pretty good. For most of the sequence, you remain above thread quality of 28, which means that you're close to an error rate of around 1 in 1,000 base pairs. Yeah, that's more or less the average error rate that you'll find in the first nearly 80 base pairs of your sequences. That's not too bad. It could be better. Yes, it could be a lot better. But in this case, it's not too bad. Yeah. So what we could consider is to get rid of all the regions that are below this threshold, like 20. All the reads that have a quality, yeah, of less than 20. They have an error every 100 base pairs. Yeah, we could get rid of them because we still have more than enough data in that data set for what we are planning to do. So per sequence quality score, basically this is the amount of sequences, yeah, that have an average quality of whatever appears on the x-axis. Yeah, so you have very little amount of sequences that have an average quality of 26 or less. Yeah, and the majority of the sequences will have an average quality of around 31, which is 1 in 1,000 base pair errors. So this is the per base sequence content. To know what's the frequency of A, T, C, and G in each of the bases in the data set that we're dealing with. As you can see, the coverage of G, the percentage of GC, it's very close to each other. The same happens with the percentage of T and A. This is because they usually pair. Yeah, you have 1 T for each A, and you have 1 G for each C. Yeah. The other thing that you'll see is that overall the proportion of GC, yeah, it's below 20%. It's around 18% in every position. Even though the basic statistic tells us that the percentage of GC it's 38%. Why is that? Because this 18% is for each of the bases. When you take them both together, it's 18 plus 18, 36 more or less. Or 19 plus 19, 38 more or less. Which coincides with what you saw on the first basic statistics. All right, sometimes in this position, in this area, you're going to see the first bases or the last bases that have very erratic sequence composition. Usually that happens, and by erratic I mean you have peaks of A's and C's and T's that overlap each other. That's usually what happens when you have primers or you have sequence adapters leftovers that need to be trimmed, that need to be removed. In this case, it doesn't look like you have any primers or any adapters left in your sequences. So the sequencing went well. Oh yeah, sorry. This is the per base GC content. As you can see, just like in the first one, in the first basic statistic, the average is between 38 and 39%. That just coincides with the basic statistics. There's not much to look there. The next one is the per sequence GC content, and this is something important. Yeah, we know that each species, well, each clade has its own kind of composition, its own GC content. Yeah, species that are very far away, they will have extremely different GC content from each other. So, if you generate first a theoretical distribution based on the number of GCs that you see in your data. Yeah, if you see that nearly 38% of your data is composed of GC, then you will say that you would assume that there is a normal distribution around that. Yeah, and that's the blue line. Yeah, And then you would expect more or less the behavior of the GC to be like that, like a normal distribution of GC along the bases in the sequences. But if you have contamination, like bacterial contamination, you will have peaks of GC content, yeah, that will look in the red line. They will look like bimodal curves. That is, you will see like a camel hump. That camel hump is a signal that you probably have contamination, or you have a combination of more than one genome. There you go. Look at this one. You have two different peaks of the percentage of the mean GC content in all your reads. That actually indicates you that some of your reads have a different GC, have a significant GC content. Yes, you will see. You will not have that kind of nice theoretical curve. Particularly when you have an isolated individual, or maybe very close relatives. Yeah, but usually if you have like a mammalian or a plant genome and a bacterial genome, which is usually contamination, you will see this kind of bimodal curves. Yeah, this is usually an indication of contamination. Yeah, and it needs to be, well, personally I like to check doing a blast. Just choose a random 1,000 reads from your data. Yeah, blast them against NCBI and see what's the frequency of matches. If I match two different species all the time, then I say, oh yeah, these are the two main species that I'm seeing on this GC graph. You have to find a way of getting rid of that data that you don't want to use, that is contaminant. Chem analysis. So, no, let's keep going to here. There we go. Per base end content. End content in Illumina reads means that the quality was so low, yeah, that they couldn't guess appropriately what was the sequence, what was the base. But we've seen already that we don't have that low quality basis. So we have 0 ends. Well, apparently there is a little peak on nucleotide 2. Yeah, but it's negligible. It's not something that's going to affect our analysis. Sequence link distribution. This is just telling you that all the sequences are 100 base pair long. This is normal because we haven't trimmed them. Yeah, and Illumina will always produce reads of the same length all the time. It will not produce like 454 used to produce reads of different lengths. No, Illumina will always produce the same amount of reads. Sequence duplication level. This actually is an indication of optical duplicates in your data. Yes. This one? In Illumina? Yes. Before you trim it, yes. Before you trim it, all the reads will be the same length. So this graph will tell you absolutely nothing before you trim it. After you trim it, yeah, then you will be getting rid of different amounts of low quality data and also different amounts of bases at the end of the reads that account for adapters. Yeah, so when that happens, the read length changes, and it changes differently for each of the reads you have, right? And that's when the sequence length actually tells you something more about how much your sequence has been reduced. Yeah, but before doing any of that trimming, nothing happens. It doesn't really mean anything. Sequence duplication level. Sequence duplication level happens when you have what we call optical clones. What is an optical clone, and why does it happen? Optical clones happen when, by chance, or by some problem during the sequencing. You remember that we talked about one single template attached to a bit, and then it was clonally amplified on top of that bit, so that you had a population of clones. Sometimes what happens is that during the amplification process, yeah, one of these templates jumps from one bit to another one that is very close to it. Yeah, so you have two bits, yeah, that will have pretty much the same sequence, because the second bit, the one that was invaded by this template, yeah, will also amplify itself, yeah, and will produce a bit full of clones of the same template as the bit that is right next to it. Usually, you can detect it by some of the Illumina naming scheme data that they give you, because in the Illumina name, they give you the coordinates of the flow cell where each read was captured, right? Remember that it was a camera, yeah, and the camera kept a record of the different color, the change of colors, yeah, in each part of the flow cell, and each part of the flow cell was meant to be one single bit, right? But if you have two bits that are very close to each other, like next to each other in the flow cell, that means that their coordinates are going to be very close to each other. And when you see that, and at the same time you see that the sequence is pretty much identical between the two records, you'd know that you probably had the issue I just mentioned. One of the reads, or one of the templates, jumped to the bit right next to it, yeah, and you've got a clonal sequencer. These are clones. These are what we call optical clones. And yeah, you can get rid of that data. They usually recommend to get rid of that data because somehow it's going to bias your results. So here, there is another reason why we have so much duplication level. Basically, it's because we have a very small genome, which is around 150,000 base pair. Yeah, and we've got 1 million reads of 100 base pairs each. So that is 100 million bases to cover just a 150,000 base pair target. If anybody cares to calculate how much coverage that is. So it was 100 million between 150,000. We have 666 times the amount of DNA, of 666 copies of the genome represented in just the forward reads. Let's not forget that we have the reverse reads that have the same amount of data. So we're talking about over 1,000x coverage for just this small, for this small genome target. Now, overrepresented sequences. Well, in this case, there are no overrepresented sequences, but basically, this usually corresponds to two things. Overrepresented sequences are sequences that appear way more often than expected from the sequence composition. Yeah, that is, if you have a GC content of 40%, yeah, you would expect that k-mers or that sequences that have a certain composition of bases would appear only a certain number of times in your whole database. If they appear more often, or if they are observed more often than they are expected theoretically, these are overrepresented sequences. This usually indicates, this is usually related to the presence of adapters in your data. And finally, k-mer content. This is kind of the same. You also have a measurement of observers expected from more normal distribution of this GC content. And if the observation, the ratio between observed and expected is way too high, these are reported. But in this case, for such a small genome, it looks more like yes. What's happening is that we have overkill coverage of these sequences, and that's what they are looking. They are appearing so often. Maybe it could also mean there was some kind of bias at the time of sampling or the time of sequencing. Yeah, but I don't think this is the case. Why? Because these reads are simulated. These are not real data. These were simulated by computer. So yeah, there's not much else to see here. So once we finish this, yeah, the next thing we want to do is to trim it. We want to get rid of low quality data, and we want to get rid of our adapters. So if you see within your files, you have adapters.fasta. Please explore it so that you can see what kind of adapters we would be expecting. Even though the FastQC report didn't show like there was any big contamination of adapters, let's just take a look around the adapters.fa, yeah, so that you can see what were the adapters used for this library. How do you do that? You can do it either with a cat, because it's a very small file, or if you feel like you want to mess around a little bit, you can use Vim or Nano or Gedit. Yep, there are two sequences only. One for the forward, one for the reverse. And this is what we're going to be looking for in our samples. We're going to be chopping. So originally I wanted to use Thermomatic because I like it better for cleaning, but it's going to be a lot easier if we use what is already present in BioLinux 8, which is called Sickle. Sickle is a program that is already installed in BioLinux that lets you do the trimming, quality trimming and adapter trimming. Since we don't know how to use it, this is the first time ever we're going to use it, let's just write it and enter. And it will give me very often, and this is a sign of kind of a half well done tool, yeah, it should give you some kind of help. It should indicate you, hey, this is the way you're meant to use this tool. So if you see, for example, Sickle asks for a command, and then it asks, the command is obligatory. You need to put a command there. Have you all already written Sickle and pressed enter? Sickle, S-I-C-K-L-E. You cannot see it from there. Now, you will see that the first line, it tells you, first, usage. You should use it like this. Write Sickle, then it tells you to write a command, and this command is obligatory. All right, so apparently it's easy to install. For some reason, most of you don't have it. You do that sudo apt-get install Sickle, and if it doesn't work, it's going to give you an error. Do you have the same error, right? You got it? Right? Okay, cool. So if you do have an error that tells you something about package manager being locked, yes, you just read that file that finishes in lock, yeah, and remove it, erase it. I'll see if I have the same issue. So just let me know if they don't let you, if you have an error installing it, yeah, just let me know. So if you already got it, try to, and this is going to be an interesting exercise, try to figure out how to use it. It's not difficult. It's actually telling you everything you need to know there. It tells you first to start with Sickle, then use a command, yeah, and then use options. At this point, you don't know what the commands are and you don't know what the options are. But right below that, it tells you command. And you have two options. You have PE, which means paired end sequence streaming, or you have SE, which means single end sequence streaming. Which one do you think applies to the data you have? Paired ends, exactly. So you now know what the command is. It's Sickle PE. Don't do anything else. Just enter, because you don't know what are the options, right? Those options that they're asking for. And here they are. Here are all the options. To use each of these options, yeah, you have to do exactly what it says here. If you want to use this option, -F, yeah, to input paired end forward FASTQ file, which is something you will have to do, you will put -F and then the name of the forward file, which will be sim1. Then -R will be the parent file 2, input parent reverse FASTQ file. Then you'll put -R, make -R space sim2 fastq.gz. Then you want to know the output for each of your the name of the output file for each of your files, because each of your files is going to be modified. They're going to remove parts of the file, the parts that have low quality, the parts that have adapters. Yeah, so you want a new name. Yeah, you can pick a name. I would personally recommend that you keep sim1.trim.fastq.gz. Yeah, and the other one sim2.trim.fastq.gz. Just to know from the name that yes, it's one for each of the files. Yeah, the parent reads. Yeah, they come in two files: the forwards or the ones, and the reverse or the twos. Yeah, you are going to analyze both files, and for each file you're going to get an output. Yeah, this is what you're doing there. You also will see that if you go further up, you will see like an overall explanation of what's going to happen. You see, if you have separate files for forward and reverse reads, use -p options, -f parent, -self reverse, -t quality type, -o or output, -p or the other output, -s trim single files. This is something that could happen, right? One of the sequences from each pair is so bad that you have to get rid of it. It is useless. So the other pair, which is still good, it's just flying. It doesn't have a pair anymore. So it goes into a group that is called the singles. Yeah, and that's where this is coming from. So -s trim singles file is those reads that lost their pairs. So if you have one file with interleaved forward and reverse reads, that is, one read is followed by its pair, and then the next read is followed by its pair in the same file, not two separate files. That's not what you've got. Then you use this other approach. If you have one file with interleaved reads as input and you only want one interleaved file as output, use this one. So basically, if it's the same case as before, don't really bother about -t or the quality type. It's the type of quality values that have been used. In this case, you're going to use the quality Sanger, which is equivalent to Cassava 1.8. Yeah, you put -t Sanger. This is required as it tells you in the help. Yeah, it would be too much. Yeah, it would be too much unnecessary explanation why we're choosing that one. Enough to say that Illumina used to use different encodings. Yeah, the most modern one is the Sanger one. Yeah, and that's the one that your sequence have. We're not using the old encodings that Illumina used to use. Well, -8 output single file. That's not what we're going to use. -q quality threshold. That's going to be important. Yeah, this is the threshold for trimming based on the average quality in a window. So basically what SQL is going to do is going to check a certain window length across your read, and when the average quality in that window drops below this threshold, yeah, that's when it's going to start cutting. That's when SQL is going to chop your sequence and cut everything from there to the end of the sequence. All right? So we have already discussed that the appropriate amount would be 20, which means one error every 100 base pairs. Then length threshold. This is the threshold to keep a read based on the length after trimming. That is, if we start with a 100 base pair read, and after trimming we get rid of 50% or more of our sequence, that is, we get a sequence of 50 base pairs, do we really want to keep it? Is it going to be useful for us? Maybe yes, maybe no. Yeah, I would say that the minimum you should keep is 70, 75 base pairs. Some people will argue that the minimum that you should keep is one base pair above the kernel you're going to use in assembly. Yeah, it's up for discussion. It's for this amount of data and the overkill coverage that you already have, over 1000x coverage of your target genome, you can be as strict as you want. Yeah, you can just be very, very picky about what sequences you keep for assembly and what sequences you don't want to keep for assembly. So yeah, let's start building our command. Please start building it while I go around and see that everybody's on the same page. So everybody got to install it, or somebody's missing? So who wants to help me here to construct my command? After Seco, what was the command I needed to use? PE. Great. After PE, what was the first flag or the first parameter I needed to adjust? -F. And we're going to use sim1. Perfect. Then the second parameter? -r. And we use the other one, sim2 fastq.gz. After that, we want the outputs, right? -o. And let's put it like sim1 trim -p would be sim2 trim. Yep. All right. So the next one. What else is required? The -t, the quality type. What quality type are we using? Sanger. Sanger. It's the reason why they have all these names. It's really silly. It's really old. It's been over 6 or 7 years since the last person or the last run had any of the Cassava 1.3 or Cassava 1.7 versions of encoding. So don't even look at those. We're using the latest one, which is Cassava 1.8, which is just called Sanger. Sanger base calling. Then we want to set a threshold, -q20. Then we want to keep a specific length, a minimum length. I recommend 75. You can use whichever you want, but don't go too low. You don't need to. So 5 prime. Don't do 5 prime trimming. That is, in every DNA sequence, you always start from left to right. Your left is your 5 prime. Your right is going to be your 3 prime. All right? Yeah. So when you say you don't want any 5 prime trimming, what you're saying is from the right end, the side that has the highest quality, I don't want you to cut anything. I wouldn't be worried about that because we already know that it's very high quality. So I wouldn't put it. Also because, where is the adapter thing? Yeah, I wouldn't touch it. If they want, if there is some sequence that have low quality in the 5 prime, just let it have low quality. Just let it be trimmed. I wouldn't stop it from being trimmed. Now truncate. Truncate is when you wanna hard cut after certain bases. Yeah, if you wanna hard cut the last 20 bases of all the sequences, then that's going to be a truncate. You're going to be truncating it, regardless of the quality. This is truncating is regardless of the quality. It doesn't matter if the quality drops or if it remains high. If you say truncate the last 20 base pairs, yeah, they're going to cut them, regardless of the quality. That's not something we would like to do. Finally, if you want your output to be gzipped or not. Since I'm already putting a gz at the end, which means gzip, I do want it to be gzipped. So -g. You can choose differently. You don't have to put it the same way. That's it. Now we just need to push enter. Means you have the -r. Yeah, I do. -f, -r, -o, and -p. -s. Yep. Yeah, the -s. -s. So let's call them single fastq gz. Yeah, we had forgotten about the single reads. Minus S, yeah. Remember that when you're trimming, yeah, in some cases you may get reads whose mate or whose pair has been removed because it didn't reach the thresholds you set. It had either too low quality, or it had too much adapter, or it was too short after trimming, so it was removed from the dataset. If that happens, then you're going to get a pairless sequence. That's going to be written to a different file, a singleton file, a file where only single sequences will go. And now it started running. We just wait for a little bit until it finishes. Remember that if you have an error, the error usually tells you what went wrong. Remember that you should be working from your INEA 05 directory, the one that you created at the beginning of the class. It's only going to take a few hours. What's the worst that could happen? It finished. Yeah, just ls. Look, it has given you some stats. Yeah, from the records you've kept over 1.5 million, which means that you're getting rid of half 500,000. Single records kept, it's 202,000. Component 1 is 166, and the other one 36. Discarded 15,000, not too bad. And single record, passive single records discarded 202,000. Yeah, it's not too bad. You're keeping a nice chunk. Near 2/3, would it be 2/3? No, 3/4. 3/4 of everything. And now you can see that you should have those trim sequences here. Sim1 trim plus Q, Sim2 trim plus Q, and also Sim single plus Q. Yeah, that's what we're going to use in the next step for k-mean analysis. So, guys, just a reminder. Yeah, all the sequencing files, all the FASTA, FASTQ, CluSTAL, all the biology sequencing files, alignment files, and all that stuff, they are always text files. They just have a different extension because there is a consensus between the bioinformaticians saying, okay, let's call this format FASTQ, yeah, and let's use the extension FASTQ, yeah. But this can be opened in a text file. The only moment you won't be able to open it in a text file is if this have been zipped, tarred, or if this has been converted into binary formats. We're going to see binary formats later on today, yeah? But if these have been converted into some other kind of format, yeah, you cannot see them in the text file. But if you have a FASTA file, a FASTQ file, if you have a FASTG file, if you have a GFA file, all of them, you can just right-click, open with Notepad, and you will be able to see and to read through them. If you see them gzipped, before doing that, you first unzip them, and then open them with Notepad. I wouldn't recommend you doing that, because these files are going to be huge, but if you want to know what they are just text files. That's it. So, was everybody able to run the program? Did it run successfully? Yeah? So you got 5 new files in your directory, right? 5? No, sorry. 3 new files in your directory. The trims, Sim1 trim, Sim2 trim, and single trim. Cool. Cool. Now, let's run the FastQC analysis again on these sequences. But let's not open the user interface. Let's do it in a different way now. Let's use the command line option. And for that, what we're going to do is we're going to write FastQC like last time, but instead of pressing enter, we will do --help. Can everybody see from the back? Just write FastQC space --help. This is a convention for most tools. If you don't know how to use a tool, either you just put the name and press enter, and it will give you some kind of help, or you just write the tool and put space minus minus help. And it should give you enough information for you to start using or to learn how to use it. So as we expected, it will give me some kind of help. Yeah, and you will see that we have several different options. Way too many options. But there is only one requirement. Oh, this is also something you may need to know at some point, but it's, yeah, well, anyway. Every option that appears between these square brackets, yeah, it's not mandatory. That is, you can put it, but you don't have to put it. You can use it, but you don't have to use it. Sometimes it's useful because it gives you a better handling of how the tool is going to work. Yeah, but the tool already has defaults, and if you don't put anything there, it will go back to its defaults, values. Yeah, for example, a contaminant file. If you don't put a -c contaminant file, if you don't put any contaminant file to look for, then this tool FastQC is not going to look for contaminants in your sample. If you put, if you don't use -f and the format FastQ, BAM, or SAM, then by default the tool is gonna expect a FastQ file, which is what we have been using. Now, if something in this command line appears outside of brackets, like segfile1, segfile_n, yeah, that means that it is mandatory. You have to put something there. In this case, the seg files would be sim1 trim and sim2 trim and single trim. Those are going to be the files. And as you can see, using the command line option, yeah, you will be able to analyze all the 3 files in a single go instead of opening each file independently. Also, you will see a lot of other options that you may want or may not want to use. I will use a few of them because my laptop, the hardware of my laptop allows me to. For example, I want to use the number of threads. I want to increase the number of threads for analysis. What does increasing the number of threads mean? That means that I can, or the program will be able to use, to analyze more sequences in parallel. Each thread is going to analyze 1 sequence at a time. And if I have 4 threads, I will be able to analyze 4 sequences at the same time. By default, the program is only going to use 1 thread. So that means that you're going to be analyzing each sequencing sequentially, one after the other That's going to take a lot longer. But that depends on how many CPUs your computer has and how many threads your computer has. All right? I think the most common is that the i5s and i7s, they usually have 4 cores, and they should have up to 8 threads, 2 threads per core. Yeah, so taking all into consideration, I would put it like this: use 2 threads or maybe 4 threads. Don't go beyond that. But yeah, let's go for it. So what are the options here? The out directory, I don't mind. You can drop it here. Minus Cassava, this is not for us. Minus extract. If set, then the zip output file will be uncompressed in the same directory after it has been created. By default, this option will be set if FastQC is running a non-interactive mode. So this option is already default. Minus JJava is if you want to set a different path to access Java, because this tool actually uses Java under the hood. No extract, do not uncompress the output file after creating it. We're not going to use that. No group, disable grouping of bases for reads greater than 50 base pairs. Well, it doesn't really affect the algorithm. Minus F format bypasses the normal sequence file format detection and forces the program to use the specified format. We could force it, but we don't have to. It will select the FASTQ format correctly. minus T threads, I've already put it. I'm going to use 4 threads. Here it tells you, for example, each thread will be allocated with 250 megs of RAM. That is, if I use four threads, I'm going to be using 1 gig of RAM. Yeah, also, you shouldn't run more threads than your available memory. Also, not more than 6 threads on 32-bit machines, because 32-bit machines have a limit of 4 gigs of RAM tops. You cannot have more than that. Minus C contaminants, well, we don't have contaminants. Minus K k-mers. This does affect the algorithm and will affect the output. Why? Because it specifies the length of the k-mer to look for in the k-mer content part of the report. Yeah, the longer the k-mer, the more time it's going to take the analysis to finish. But it's going to be also more sensitive to what you want to find. Also, it must be between 2 and 10. Yeah, I would leave it as default, which is 7. Yeah, it works pretty well. Oh no, 5. 5 is the default. And then quiet is if you don't want, if you want it to run silently until it finishes and produces all the data. So just this, and then sim1 trim, sim2 trim, single trim, single, okay, that's it. And then it gives me some information. It's starting the analysis of each of the 3, 5, 10, 15, until it finishes. The report I'm going to get is also going to be an HTML. For me, this is usually faster than. Don't be afraid. You can make up. You can actually rewrite the command from what you see in the help. The basic command is just to write fastqc space and all the files that you want to handle. The minus T4, it's in my case because I have the memory and the threads to run it. You should be aware of what your hardware limitations are before you start playing around with that. Those who have i7s, they can do it. Those who have more than 4 gigs, they can play around with the minus T4. Yeah, if you don't, or if you don't know, you better don't do it. Yep, so after it finishes, it has created 3 new directories. Right? Please open, just like you would in Windows, please open the files. On your lateral dock, open your files and go to INEA 05. Documents, INEA 05, and you'll see that you have 3 new directories, one for each of the files that you use. Just open the first one, and you'll see there's a fastqc report. For the next exercise, we really don't need to be that much more efficient. We have more than enough data. So don't worry about repeating SQL, but if you want to repeat SQL, yeah, if you want to be more strict about how you trim it, just feel free to play around. I think it's time for lunch. Yes? So we'll come back, yes, we'll come back to, after lunch, we'll come back to keep going with the next session, k-mer analysis. Oh, yes, before we leave, please check the following. Write this on your command line, just to make sure that we all have the program. Because it should be default in I don't know what happened with SQL, it should be default, installed by default in your BioLinux 8, that's why I chose it. And I have it by default, but for some reason, neither of you did. So this is the other one, jellyfish. Just run jellyfish minus help, and you should get some help, right? You know that you have kind of like a minimum length of primer so that you make the priming site as unique as possible, right? The longer the primer, the more likely it's going to be unique in the genome. Yeah, this is pretty much the same idea we have when we select a k-mer size. Is that we want it to be as unique as possible in the genome. so that repeat regions don't mess around with it, or we can detect them more easily. All right? So something between 23 and 32 or 31 base pairs or k-mers should be enough and should fit your memory. Yeah, but we're still gonna play around and see if we can use something smaller. I've seen k-mer analysis done with 17 k-mer size. Yeah, but please first check that you all have jellyfish. Yeah, if you have a reply when you do jellyfish -- help and it's not an error, the jellyfish command doesn't exist, then you're on the safe